So here I listed out the common criteria levels. So we have 1 through 7. 1, we're functionally tested. Number 2, it's structurally tested. 3, we have methodically tested and checked. So we're getting stronger and stronger here. 4, methodically designed, tested, and reviewed. Number 5, semi-formally designed and tested. 6, semi-formally verified, designed, and tested. And then 7, it's formally verified, designed, and tested out. So we want to strive for the higher levels, obviously, but we have to start somewhere, right? So you can start at the lower levels and move your way up and get it more secure and stronger, harden it down, if you will, so it can meet the higher common criteria levels that you may need inside of your organization. So some common criteria terms that we need to be familiar with. Target of evaluation, or TOE, T-O-E. That's the system or the product that's being evaluated. Kind of makes sense. If that's our target and we want to evaluate it, that's our target of evaluation. So that's what we're going to put through the ringer to see if it meets our common criteria. Then we have a security target. Now this is the documentation describing our TOE, including the security requirements and the operational environment of that target of evaluation, of where it's doing what it does, right? Whatever kind of operational infrastructure it's in. We have a protection profile. This is an independent set of security requirements and objectives for specific category of products or systems, like firewalls, IDSs, for example. The evaluation assurance level, the EAL that I mentioned a minute ago. That's the evaluation score of our tested product or our tested system, that target of evaluation. And then finally we have the PCI, right? The payment card industry, and then DSS, Data Security Standard. We need to be familiar with this. This is a security standard created by the payment card industry. Now the council, these folks, they're made up of, mainly the big credit card companies that we have worldwide, like Visa, MasterCard, American Express, Discover's out there. There's some other ones out there, and then people, from banking industries and other Fortune 500 companies could be sitting out there on this council as well to give their input to make sure they're secure. But it was the credit card companies that came together and said, hey, something's got to be done. We need to make sure that we're protecting this data. So anybody that handles any type of credit card transactions, if you do tens of thousands of them a day or just one, you have to follow this PCI. So it's requiring vendors to use these specific security precautions that they have listed out inside the PCI. Now let's talk about the security capabilities of information systems, of IS. First off, we have something called hardware segmentation. So if we think of software and hardware, software is the applications, operating systems that we put on a computer. Well, we put that on top of our hardware. So what we can do is segment our hardware the way it's programmed inside. So this takes process isolation a little step further. Instead of isolating our processes internally, like the operating system would be responsible for that, we can provide more security than those logical processes by separating out our hardware now. You may have separate processors for separate processing or processes that you need to take care of. So you could segment that hardware out. So you could have 8 processors in a server, and these 2 processors take care of this, and these 2 take care of that. So you could actually segment out the hardware that way, keeping processes separate. Too many processors in there, huh? We have memory protection. This prevents one process from affecting the confidentiality, integrity, or availability of another. So everybody has their own little memory space that they run in. So this is a requirement in, say, our multi-user environments, multitasking, if we're running more than one process simultaneously, which we always do anymore, right? I mean, even if you don't have more than one application open on your system, I'm promising you there's some stuff running in the background that the memory those programs are loaded into memory is what I should have said. So let's say you have a web browser opened. Well, that web browser is running in RAM or your memory. But so is all the other background processes. But we don't let them overlap each other, so we don't want them affecting what the other one is doing. They're running in their own memory space. All right, so that way we don't have confidentiality integrity problems, but we could have some vulnerabilities when it comes to that, like buffer overflows, for example. All right, if we have memory protection in place, but somebody can compromise our application, they may be able to take up more memory than what was allocated to them by this memory protection. They say, well, you get 10 megabytes, which is not anything, but 10 megabytes of space to do whatever it is you need to do. Okay, great. But if I try to shove 11 in there, I'm going to force buffer overflow, and I could do a couple things, like a denial of service attack. That's the availability on everything else in there. Or I could maybe run some malicious code, have another process called because of that exception, that error that's going to be thrown at us. We can also do that process isolation. I kind of mentioned that with the hardware segmentation. Now, this is a logical control, and it attempts to prevent one process from interfering with another. Again, kind of like with the memory, right? We have dozens of things running in the background, but if one of those crash, we don't want it to crash the whole computer. Now, this is pretty common in multi-user operating systems, Linux, Unix, Windows operating systems, because if one process crashes, we don't want it to bring down the whole system. We want to be able to recover from that. So we say, okay, you run in your little process space, you run in your little process space, you run in this one. So if this one crashes, dies, gets corrupted, whatever, it doesn't affect everybody else running on that processor. Same way with our memory that we just talked about. Now, no process isolation means a crash in any, say, MS-DOS application could crash the entire system, because MS-DOS, older operating system, we're reaching way back here, didn't have process isolation. And that was kind of a problem, because if one little thing crashed, it didn't matter what it was, everything was gone. Now, think about fast forward to today and all of the processes that are running in the background. I think when I boot up my laptop, I have maybe 70, maybe that's a little high, 50 or 60 processes running before I ever open an application. It's running all these little things in the background that's supposed to make the computer better and faster and a better user experience, right? But if one of those crashes, let's say something with the video or the sound, or one of my Dropbox or Google Drive, one of those, what if that crashes? There's something that happened, right? I got the latest update, but there was integrity problems, and I didn't get it all the way, and it causes a crash. Well, if that one crashes, I don't want it to crash my whole entire computer just because of that one application. I want to be able to terminate that one application and maybe restart it if I need to use it again, right? So if you think about that, I mean, we'd be crashing all the time probably, right? I know people that they're like, well, Windows crashes all the time anyway. But that would be bad, right? It'd be terrible for like data users if a background application was to crash and it crashed the whole system. Well, they may not be at a saving point, or something might have happened. I mean, there's just tons of things that could happen without process isolation. Now, Mr. Reference Monitor here, he's a pretty busy guy. This is a core function of the kernel. And the kernel is pretty much the brain of your system, right? All the way down to kernel level. We got different rings. There's 4 different rings in an Intel kernel. And the very middle ring is what we consider like the brain, right? If we can compromise that as an attacker, I own or pwn the whole computer, right? So again, the reference monitor, his core function of the kernel is running the reference monitor, which mediates all access between subjects and objects. He's the go-between. All right, it enforces the system's security policies that you've set as a system admin, like preventing normal user from writing to restricted file, like a system password file, for example. So he's a pretty busy guy, and pretty good for us too when it comes to security professionals as well, because he's the go-between, right? Between the subjects, again, the users sitting at the keyboard or interacting with that system, and the objects that they are trying to affect. So he's trying to keep everybody in line and keep everybody, the traffic cop, if you will, of what's going on. And then virtualization. Virtualization, we know that adds that software layer between the operating system, whichever one you're using. If you've got a Linux box there, you could put some virtualization software on there, like VirtualBox. And then when you do that, you put that software on top of your operating system, that allows you to talk to the underlying hardware. So you can have a guest operating system or a VM running inside a VirtualBox that's sitting on top of your physical computer or your host computer. And again, you can have many virtual machines running at the same time, depending on the resources, because they all take some resources. Well, if you have two virtual machines and you put Linux on one and Windows 8 on another, you're going to have to allocate hard drive space for each operating system, allocate memory for each one. All right, you can allocate and segment out how much CPU cycles they get. How many cores does one get, or how many threads does another one get? So you can figure that out. You can set all that up as well inside your virtualization to keep things separate. We also have something called a constrained user interface. These are pretty nice because it helps us as security professionals. We're not allowing end users to see something they're not supposed to see. So we're limiting what the user sees on the screen or the display by using, say, data views from a database, or just allowing certain menus for that particular user. So I'm trying to think of a good example here. In Office 365, for example, I know when I log in, I have a different interface, different menu system than, say, some of anybody else in my organization when they log in, right? I have an admin button up there, right? A little gray button with a cog on it where I can get in and do administrative stuff. Some other users, if they log in, they don't have that administrative button. They can't even see it because of the constrained user interface and permissions. They just can't see what's going on. And if I don't have them licensed for particular software, they won't see that either. You may see what the user sees on the screen as far as like an automated teller machine, right? Depending on how somebody logs in. If a tech comes in, they may get more options than, say, a regular user. Right? We put in our card, put in our PIN. We only see, withdraw, check your balance, or I don't know. I don't go to the ATM very often, but you got different options in there, right? And depending on which ones you pick, then you see a different menu and then a different menu. We also have fault tolerance. All right. Now, fault tolerance is just it's a good idea. I'm not going to say it's a must, but it's a great need, I guess, if I can say that. Now, this is for systems within organizations to be able to continually provide operational availability. Now, they got to be implemented with fault tolerance in mind for that to happen. So you think of fault tolerance, you might think of redundancy. If you have directory services, you may want more than one server running directory services, because if something happens to server number 1, you still have server number 2, and people will be able to log in, and you'll stay in production. When it comes to database servers, you may want some fault tolerance. You can have more than one on the back end there to service all those requests. You may have fault tolerance in your front-end web servers. You may have fault tolerance power supplies. You may have fault tolerance in your hard drives. You may have fault tolerance in your network. Have redundant firewalls, redundant switches, redundant routers. We can have redundant everything. But the more redundancy we built in, what is that going to do to the bottom line? Right, that all costs money, right? So you're designing out the latest and greatest network, and you've got double everything. You've also got double the cost. So when you slide that over to Mr. CIO or Mrs. CEO, they may say, no, we're not paying for all that. You need to come up with another design. So you'd have to figure out which ones you want, but fault tolerance is a great idea when it comes to keeping your network going. Now we also have something called the TPM, Trusted Platform Module. Now this is a hardware module for data encryption. It's on most, if not all, the motherboards nowadays that come out. So if you go buy a new computer, more than likely, I'm not going to say with 100% certainty, even though I've seen articles and forums say that, it should have this TPM chip on there. And that's hardware encryption. So what that means is it's tying, say if you do whole disk encryption. I go buy a brand new laptop and I do a whole disk encryption. It ties that hard drive with that TPM chip that's soldered right on the motherboard. I mean, it's not, people, I guess you can, but it's not going to be the easiest thing to go take that TPM chip off if you want to take that hard drive. Most people don't have that kind of time. If I'm going to steal a hard drive, I'm going to go in there and get the hard drive and leave. But if we've encrypted it with that TPM chip, that module, it's useless. Because of the encryption, all the keys, everything is stored on that module, on the motherboard, on the computer. So even if I was to take that hard drive out and throw it in another computer and plug it up, or put it in a cradle, or put it in a case and put a USB to it and plug it in as an external hard drive, it's gonna, I may see the data, but again, it's gonna be all encrypted. It's not gonna do me any good. It may not even let me access the data at all without the proper encryption keys. So Trusted Platform Module is a cool little deal. Now coming up, next we'll continue on with Domain 3, and we're going to continue on starting with assessing and mitigating the vulnerabilities of security architectures, designs, and solution elements.